In this video, I'll explain what are eigenvalues and eigenvectors of a linear transformation or of a matrix associated with linear transformation. Let me consider simple linear transformation T given as T of x comma y equal to x comma minus y. This is nothing but reflection of a point with respect to x-axis, reflection of a point in plane with respect to x-axis, and this is a linear transformation. Now we have to find out first the matrix of linear transformation. Matrix of linear transformation means you have to find out after applying this transformation where the basic vectors, standard basis vectors, they are nothing but 1 comma 0 and 0 comma 1, I cap and j cap, where they will land. What is the new position of these unit vectors in the direction of x and y axis go to? So I will apply the transformation, this transformation. So 1 comma 0 will go to 1 comma 0 itself. It won't change its position. It will be at the same position. Now 0 comma 1 will go to 0 comma minus 1. So it will come here 0 comma minus 1. So this is the new position of I cap and this is the new position of j cap. Hence, matrix of this linear transformation is nothing but where I cap and where j cap lands, new position of I cap and j cap after applying the given linear transformation. So I cap goes to 1 0 and j cap goes to 0 minus 1. This is called as the matrix of linear transformation. Therefore, eigenvalues and eigenvectors of linear transformation is same as eigenvalues and eigenvectors of this matrix A. Matrix is a tool to perform all the operations which are related to the given linear transformation. Now, in after applying this linear transformation, you can see that I cap is at the same position, or else let us write the span of this vector 1 comma 0, which is nothing but lambda into 1 comma 0 set of all those vectors which are multiples of 1 comma 0 where lambda belongs to R. That is called as the span of the vector 1 comma 0. That is nothing but span of 1 comma 0 is entire x-axis. Okay. Now you consider any other point like span of 1 comma 1. Span 1 comma 1 point is here. Span of 1 comma 1 is lambda into 1 comma 1 such that lambda belongs to all multiples of 1 comma 1. They are nothing but span of 1 comma 1 is the entire line. Okay. Now there are few vectors which after applying the transformation will go out of their span, and there are few special vectors even after applying the transformation they will be in their own span. See, for example, 1 comma 1, this is the vector. Apply this transformation 1 comma minus 1, so that vector goes to 1 comma minus 1. So span of 1 comma 1 is entire line. Now it is going out of its span. Most of the vectors behave like that when you apply the transformation. But look at this vector. Span of 1 comma 0 is nothing but entire x-axis. Even after applying that transformation, it will be on its own span. 1 comma 0 will be on the x-axis only. It has not changed its position. Okay. Now you can consider one more special vector, that is 0 comma 1. Span of 0 comma 1 is equal to set of all multiples of 0 comma 1 such that lambda belongs to R. So in this case also the span of the vector 0 comma 1 is entire y-axis. After applying the transformation, it has not changed its span. It is remaining in its own span, but the position is changed, but it has not moved out of its span, whereas this vector 1 comma 1 has moved out of its span and it has taken the new position 1 comma minus 1. But 1 comma 0 is in its own span, 0 comma 1 is also in its own span. So these are the special vectors which are not going out of their span even after applying the linear transformation. Such vectors are called as eigenvectors, and by what amount the new vectors will get stretched or squished is called its eigenvalue. See, in the first case, 1 comma 0 is at the same position, 1 comma 0, though it is in its own span. Some of the vectors will get stretched, like 1 comma 0 goes to 2 comma 0. 1 comma 0, if it goes to 2 comma 0, it is in the same span, but it gets stretched. In that case, eigenvalue is 2. But now here 1 comma 0 is in its own span, but it is at the same position, 1 comma 0. Therefore eigenvalue is equal to 1, corresponding to this vector. Similarly, corresponding to 0 comma 1, eigenvalue is minus 1, because though it is in its own span, it gets squished up by an amount equal to minus 1. Therefore, another eigenvalue is minus 1. So, the eigenvectors corresponding to the eigenvalue 1 are all the points on the x-axis. So, I will name this k1, 0. The eigenvectors corresponding to the eigenvalue minus 1 are all the points on the y-axis. I'll name them as 0, k2. Okay, where k1 and k2 belongs to R. So these are called as eigenvectors, and the corresponding value is called as the eigenvalue. This is the importance of getting eigenvalue and eigenvector for the given linear transformation. But algebraically, what we do is, every time we can't map like this is for the understanding purpose. You have to find out those vectors which are remaining in their own span, and you have to find out that value by what amount it gets stretched or squished. That is called its eigenvalue. I will give you one more transformation to illustrate this. T of x comma y equal to 2x comma x plus y. This is one more linear transformation. So in this case, first get the matrix of this linear transformation. Means matrix of linear transformation is where I cap lands and where j cap lands after applying the transformation. So apply. What t of 1 comma 0 is, t of 1 comma 0 is 2 into 1, that is 2 comma 1 plus 0, it is 1. Now that will go to 2 comma 1. This is the new position of I cap 2 comma 1 after applying the transformation. Now after applying this transformation, 0 comma 1 will go to 0 comma 1 goes to 2 into 0, so 0, and 0 plus 1 1. So 0 comma 1 will remain at the same position, 0 comma 1. This is the J cap after applying the transformation. Therefore, matrix of the linear transformation is I cap goes to 2, 1, column wise you have to write, J cap goes to 0, 1. This is the matrix of linear transformation. Now you have to search for the special vectors which remain in their own span even after applying the linear transformation, and you have to find out the value by which those remain in the same span, but whether they get stretched or squished or remain same, that you have to find out. That particular value is called as eigenvalue. So you take any vector like 0 comma 1 only, you can say directly it is that special vector. Now span of 0 comma 1 is nothing but it is equal to multiples of 0 comma 1, lambda belongs to R, which is nothing but entire y-axis. Now after applying the transformation, 0 comma 1 is not moving out of its span, and it didn't get stretched, it didn't get squished also. It is in the same position. Therefore eigenvalue equal to 1, and eigenvector is corresponding to that eigenvalue, all points on the y axis. 0 comma 2 also, after applying the transformation, t of 0 comma 2, that goes to 0 comma 2 itself. Therefore 0 comma 2 is also a special vector which doesn't go out of its span, and eigenvalue, corresponding eigenvalue is 1. Now I cap that is going out of its span. 1 comma 0 goes out of its span, because span of 1 comma 0 is entire x-axis, but it is going outside its span. It goes to 2 comma 1, this point, hence it is not a eigenvector now in this case. Therefore, which are the other possibilities that you have to check? So you can check span of 1 comma 1, lambda of 1 comma 1, where lambda belongs to R. So this is the point 1 comma 1. Now span of this 1 comma 1 is the entire line. Therefore, after applying the transformation, where 1 comma 1 goes to, let us find out that. That is 2 comma 1 plus 1, 2. So 1 comma 1 goes to the new point now. This is the point 2 comma 2. So 1 comma 1, this is that vector, after applying the transformation, is not leaving its own span. Okay, this line, span of 1 comma 1 means entire line. So the after applying the transformation also, the vector is in its own span, in upon this entire line only. But now in this case, it gets stretched up by an amount equal to 2. 1 comma 1 goes to 2 comma 2. Similarly, 2 comma 2 goes to 4 comma 4. 3 comma 3 goes to 3 comma 3 goes to 6 comma 6, and so on. Therefore, eigenvalue equal to 2 and the corresponding eigenvector, which is equal to the points on the line y equal to x, that is k comma k, where k belongs to R. So this is how we define the concept of eigenvalues and eigenvectors. Eigenvectors are the special vectors which do not go out of their own span even after application of the transformation. Eigenvalue is that amount by which the vectors will get either stretched up or squished up based on the given linear transformation. That was the geometrical explanation. Now, algebraically, what we do is, algebraically, any transformation. I had considered the first transformation as reflection, x comma minus y. This was the transformation, and matrix associated with this transformation is given by 1, 0, 0, minus 1. This we already found in the beginning. Now, algebraically, what we do is, when you want to find out eigenvalues and eigenvectors, we have to find out those transformation, those vectors. Now, transformation is represented by this matrix. So A into any vector is equal to lambda into V. Span of that vector is denoted as lambda. So after applying the transformation on this vector, if it is equal to lambda into V, means if it remains in its own span, then we call that vector as eigenvector, and the corresponding value lambda is called its eigenvalue. So it is AV minus lambda V equal to 0, which is A minus lambda into I into V equal to 0. It is a homogeneous system. Now, to solve this homogeneous system, it always has a trivial solution. So we are considering eigenvector as non-zero vectors. We want the non-trivial solution other than zero solution. That exists only if rank of A minus lambda I is less than the number of variables here, in the number of points in the given tuple V. Okay. So if number of variables, that means if that happens, rank is less than the number of variables happens only if determinant of A minus lambda I equal to 0. Therefore, we call this as the characteristic equation. So to find out the eigenvalues, algebraically what we do is equal to 0. We will find its characteristic equation. So that is 1 minus lambda 0 0 minus 1 minus lambda equal to 0, which gives you 1 minus lambda. You can take minus common, 1 plus lambda equal to 0. This is lambda equal to 1 or lambda equal to minus 1. Therefore, eigenvalues are 1 and minus 1. The same thing we got here geometrically. See, lambda equal to 1, lambda equal to minus 1. These are the two eigenvalues. Now, to get the corresponding eigenvectors, algebraically what we do is we have to substitute here a minus lambda is 1 into I into that vector v. It is a two-dimensional vector, so I'll take x y is equal to 0, a minus I. So this is the matrix A. From this you subtract I, that is 1 minus 1 0 0 0 minus 1 minus 1 minus 2 into xy, which is equal to 0. So this gives you 0 into x minus 2 into y equal to 0. So this gives 0 into x minus 2y equal to 0, which gives 2y equal to 0. So which implies y equal to 0. Therefore, x can be any value, but y value is always 0. So this is the eigenvector corresponding to the eigenvalue lambda equal to 1. Similarly, lambda equal to minus 1, for this case, a plus I into x equal to an xy equal to 0. So a plus I means 1 plus 1 2 0 0 minus 1 plus 1 0 into xy equal to 0. So this gives you the system 2x is equal to 0 implies x equal to 0. So in this case, x is 0, y can be any value k belongs to R. Therefore, eigenvector corresponding to the eigenvalue minus 1 is of the form 0, comma k. The same thing we had explained here. I had taken k1, k2, that's it. You can mention any other variable. Eigenvector corresponding to the eigenvalue 1, we got it as k1 0, corresponding to the minus 1 value 0 k2. So this is geometrically, this is algebraically, we find the eigenvalues and eigenvectors of the given matrix, which is same as finding eigenvalues and eigenvectors of given linear transformation.